This is the third lecture. In the first one, we covered all preliminaries on quantum algebra, monoid categories up until modular categories, fusion categories. And the second one, we talked about surgery approach to three-dimensional TQFTs and the corresponding Witten-Reshetikhin triad invariants of closed-oriented three-manifolds. Today, we'll study different approach, state sum approach to three-dimensional TQFTs and corresponding triad Viro Barrett Westbury invariants. So this is, I should mention beginning that initially these invariants are discovered or studied by Tribe and Viro, but they study specifically again UQSL2 and in a kind of more specific, in a specific setting, and they proved it from a triangulations of a three-manifold. They derived a numerical invariant, and later Barrett and Westbury, they give the most general version of this algebraic setting to they derive this invariance from any spherical fusion category. There's like two completing works of each other. That's why it's in general they abbreviated. Like last lecture, I wrote VRT invariance as an abbreviations. This time in general, people abbreviate as expected like this. Well, in the first lecture, we covered the first part of this book of Vladimir Tribe and Alexey Viradizier. And the second one, we went back to Tribe's blue book, the classic quantum topology book. And then we have seen operative invariants of ribbon graphs and associated with Reshetikhin Tribe invariants. And today, we're going back to this book. This time, we jump to the third section because the second section is completely algebraic and it's not necessary for our purposes at the moment. But first, we will focus on this. Mainly, I will focus on this chapter 3. I will say at the end something about graph topological field theory, in what sense it is follow-up of this theory, and then make a hopefully connection between these two theories. Well, I will not make the connection. I will just state the connection, what it is. It's a deep theorem, and hopefully we will see some unified picture of these invariants somehow. Okay, let's start. I want to start with a little bit from last time. Towards the end of the last lecture, I talked about axiomatic definition of TQFTs, and then from this I derive some properties. We can today derive even more properties maybe. Well, Siegel defined conformal field theory kind of axiomatic way, and then afterwards Atiyah, in a similar way, he attributed collection of certain number of axioms, like closed manifold is assigned to some number, manifold with boundary assigned to some dual vector space, a vector in a dual vector space, and so on, which behaves under Gaulian well. But all these axioms that Atiyah listed back then, like late 80s, I guess, they can be collected into single phrase. A TQFT, a three-dimensional TQFT, or more general n-dimensional TQFT is a symmetric monadal functor from cobordism category to the category of vector spaces. We are interested in three-dimensional TQFTs. And let's recall what is this category. This category has closed-oriented surfaces as objects, and morphisms are three-dimensional oriented cobordisms but we consider them up to diffeomorphisms relative to the boundary so that we have well-defined composition. And target category is even simpler from linear algebra. Category of K vector spaces. Anamorphisms are just K linear maps. Let's pick K as it's just a field. Anyway. Okay, let's recall again what is the functoriality of this functor, this TQFT. So when we are given two surfaces, okay, these are objects under a functor, this object maps to another object. So sigma 1 is mapped to some vector K vector space, V sigma 1. And similarly, another vector space, another close oriented surface. Maybe I should put orientations. Everything is oriented to emphasize that. So sigma 2 and another close oriented surface to another, it maps to some other K vector space. And whenever we have a morphism between them, so morphisms map to K linear maps, so we expect that this whole three-dimensional thing, we don't know what it is a linear map between the corresponding. And whenever we cut through some codimension 1 close-oriented surface, this W, in like pictorially like this, that means we write this three-dimensional cobordism as a composition of two cobordisms. And each of these cobordisms are going to give some maps between the corresponding vector spaces. And functoriality, because this cobordism is composition of these two, functoriality of TQFT implies that this invariant is equal to this composition. Well, this was the functoriality property of C. That's what it is bringing. It says this whatever these vector spaces are and invariants coming from TQFT, they behave well under pooling. And another structures on this category is the monoidality of C. So remember, COP3 are the monoidal product in COP3 taking to chain union, and unit object is empty surface, and in the target we have taking vector tensor product over vector spaces, and unit object is the one-dimensional vector space. Now there are two conditions on a monoidal functor. Remember, this consists of Z0, C2 from the first lecture, and the first one is preserving the monoidal structures. When we take this union of surfaces, so there is an isomorphism between the image of the union and the tensor products of individual images of the individual ones, because these are all elements. Objects are. This is an object of a cobordism 3, and this is an object of cobordism 3. And similarly here we have similar property. They are coming from this Z2 component of symmetric monoidal functor. And in the same way, when we have cobordism, they are disjoint union, so their images are again functorially tensor product of the corresponding parts. Well, another property that needs to satisfy to be a monoidal functor, it needs to preserve the unit. So if you consider closed-oriented 3-manifold, well, let's they have some surfaces, spheres, and bounding, non-bounding, whatever. Any closed 3-manifold in this category, COP3, whenever we have closed 3-manifolds, it's regarded as a cobordism from empty manifold to empty manifold, which is the unit object for disjoint union operation. Since there is no boundary, that's the case. And then under Z, Z0, the part of the symmetric monoidal functor relating to units, image of a unit with the unit of the target category, we must have some isomorphism between image of empty manifold with the unit object of the category vector spaces. And in this case, such a linear map between rank 1 vector spaces is determined by the image of the unit of the vector space. And that's the invariant that we associate the TQFT. That's the numerical invariant. So this is the numerical invariant. That's the kind of quantum invariant associated with closed-oriented n-dimensional manifolds, or in this case, it's 3-manifold. And whenever one has such a numerical invariant of closed manifolds such that it is multiplicative, and we take this union of with another one, it's going to give tensor product with this one. But tensor product of numbers is just multiplication. So one asks, whenever we have a multiplicative invariance of closed manifolds, and then which is multiplicative with respect to this union operation, one asks, can we extend this to a functor? And the same way, when both Wittgenstein triad and triad zero, those invariants, when they're fine initially for, of course, the numerical invariants, and then people try to extend them to a TQFT. Well, this category is a more structure. It is in fact a spherical category. Remember what was spherical means? Spherical means pivotal category. Spherical category is a pivotal category. And for all endomorphisms, left trace equal to right trace. For all left trace of F equals to right trace of F for any endomorphism. And remember, pivotal means it's a rigid category that every object admits left and right left and right duals, and they coincide. But pivotal category comes equipped with this duality, these duals. Not only they admit, but the objects have their duals, and the left and right duals coincide. So let's see. Okay, for any closed-oriented surface, sigma, we call, what is the unit object in this category? What is the identity morphism from the sigma to itself? Is the diffeomorphism class of sigma cross I. That's as expected. Now, what is the duality? Like, we are going to define a pivotal structure. Whenever we are given as surface, sigma, closed-oriented surface, what is its dual? Its dual is the orientation reversed version of it. And so what are the duality data? Duality data is exactly like taking this this cobordism and like turning back to the bottom. This is a morphism, sigma, this union minus sigma to empty manifold, which is exactly the morphism definition of an evaluation. So target and source of the same evaluation, it makes sense. And similarly, co-evaluation is the flipped version of this. So one is to check next what? The duality data, the zigzag equations that we have seen before. And in this case, they are precisely this, geometrically. Saying that this is evaluation and co-evaluation for an object sigma in this category says this one, this cobordism, the union of cobordisms, is equal to, and similarly, there's one more, I didn't draw it. There's a flipped version of this vertical, with respect to vertical axis. There's another one. So they must be equal to identity morphisms. Exactly. This composition must be equal to, right? That's another reason why we need to consider diffeomorphism classes of surface, diffeomorphism classes of cobordisms on the morphisms. If we don't mod out here, if we don't if we don't do this, then it doesn't work. These two cobordisms are diffeomorphic relative to boundary. When we fix their boundary, one can find a straightforward diffeomorphism, but they're not the same. They're not the same morphisms. But in the equivalence classes, they agree. This is precisely sigma cross I, the identity, which is identity of sigma in COP3. So this is the pivotal. This shows that it's a pivotal category. So every object admits a dual, and then we equip every object is equipped with this duality data, evaluation, co-evaluation. For every closed manifold, this is the to all the data. It's kind of unique. So next we need to check sphericality. So let's take any endomorphism from sigma to sigma. If we consider W any endomorphism from sigma to sigma, it's going to be of this form. So what is a trace? Its trace is co-evaluation on the right. Left trace is co-evaluation on the right applied V, on the left applied identity, and then we have evaluation. And it's diffeomorphism class of this composition. And so what is right trace of such a morphism? It is given precisely co-evaluation on the left we apply W, and on the right we apply identity, and then on the top we have evaluation morphism. And these are clearly diffeomorphic manifolds. So they agree. They don't have boundaries, but they're diffeomorphic. It's just a swapping, right? Just a swap, reflecting. So this kind of short proof of maybe just observation of this statement, why it's true. But then if we have spherical category on the domain, and we know that vect is a spherical category where every object, this is just usually linear, every object is dual is V star, and then evaluation and co-evaluation, right? Co-evaluation is just about picking a basis, okay? Then because every vector space, in terms of pivotal structure, everything comes with a basis. And then the theorem says for any three-dimensional TQFT, it's not only a symmetric monoidal functor, but it's in fact a pivotal functor. So what does that mean? It preserves the pivotal structures in here. It preserves the duals. So whenever a sigma closed-oriented surface mapped to Z sigma, its dual, which is minus sigma, it is mapped to dual of the vector space of what is assigned. And dimension of this vector space is precisely the sigma cross circle. It's like mapping torus of identity. Yeah. So this has, in particular, one implication of this result is that whenever we have a TQFT, right, for any surface, QFTZ, and for any surface, sigma, Z sigma must be finite dimensional. Okay, because this is dualizable, and this functor is pivotal, so it preserves duals. So in particular, its image must be dualizable in the category of vector spaces, and only dualizable objects in the category of vector spaces are finite dimensional ones. So whenever we have a TQFT, its images of surfaces are finite dimensional vector spaces, images of objects. So state sum, like surgery TQFT, use surgery representation of 3-manifolds. It take advantage of this structure representing, Licorice-Wallace theorem says every closed-oriented 3-manifold can be represented as a surgery along a framed link on S3. Now we are using another fact, another way of understanding 3-manifolds, more combinatorial maybe, is the triangulations, kind of a generalization of triangulation. Every closed-oriented 3-manifold, and also 3-manifold with boundary, can be triangulated. And the polyhedrons and the skeleton that we're going to define and use skeletons when we define the state sum invariance as a more general way of doing it. It's again every triangulation gives rise to a skeleton, but skeletons are more general and they're better for doing for making computations of state sum invariance simpler. Okay. Okay, a two polyhedron is a compact topological space that can be triangulated using a finite number of simplices of dimension 2. So as we have compactness, and which can be triangulated using simplices of dimension 2, and the condition is that all 0 and 1 simplices are faces of two simplices. So consider this. This is not a scale 2 polyhedron. This is not a 2 polyhedron because these one simplices and 0 simplices are not faces of two simplices. Similarly, this one. Because of these reasons, this diagram is not a 2 polyhedron. Yes, it consists of simplices of dimension less than 2, but it doesn't satisfy this condition. On the other hand, this one is a 2 polyhedron. Every 0 and 1 simplex is a face of at least 1 2 simplex. Now, when we have a 2 polyhedron, we study their stratification. A stratification of a 2 polyhedron P is an unoriented graph embedded in P, embedded in 2 polyhedron, such that when we remove the interior of P, that means when we remove this interiors of regions that we will see, we get this graph is embedded in when we remove the interior, this whole thing is embedded in the G. So for example, when we take this example, so what is an example of an stratification? If you consider just this one skeleton, right? It is definitely like taking G as blue one. G is blue with blue colored part. Then this is definitely a this is definitely a this is definitely a stratification of G, because when we remove the interiors, which are all these regions, this whatever remains is in fact equals to G. Not only that, but equals to G in this case, this example. So when we are given a stratified polyhedra, then these parts are called regions. These interiors of two simplices are called regions. And when we fix a vertex, a branches at a vertex V is kind of germ of these regions that are in the neighborhood of this vertex. So germs is important. It's not only that how many regions are there, it's about germs of it. For example, this one. This is a stratified 2 polyhedra. So this is kind of stratification at the moment, and we have a vertex here, let's say. Vertex. So this is one germ, this another, but here we don't have one germs, we have two germs. And we look at the neighborhood around this vertex, there were one coming from this side and another coming from this side. Even though there is a single region, there's only one region, but number of branches at this vertex is 4, not 3. Even though there are three regions, but 4 branches at V. This is about local, how many local germs of regions at that vertex. So let's see some examples of these regions and branches. So just consider triangulation and be a closed oriented 3-manifold, and T be its triangulation. Okay, if you consider the first two scale, if you consider two skeleton of it, and this is a stratified polyhedra. Where stratification is the graph is T1. So we only consider, we get rid of all these three balls, these three-dimensional balls of this triangulation. We just look at its two skeleton, and if we look at just two skeleton, and in this skeleton, the boundaries of this two skeleton, each triangle is going to be of this triangulation is going to be stratification of this polyhedra, two polyhedra. This is an example. Any triangulation of oriented three-manifold gives rise to stratified polyhedra. And regions are precisely the faces, two faces of these triangulations, these simplices. These are examples. And for any vertex, in this case, it seems okay. Like there's no tricky part. Like number of branches here is 1, 2, 3, and 4. And similarly, this part, there are 1, 2, 3, 4, and the one backward is like 5. There are 5 branches at this vertex. And now, if we consider this is another stratified two polyhedra, and these colored regions are the regions. These colored pieces are regions. Like they're all, how many regions are there? There's 1, 2, 3, 4, 5, 6. And this is the vertex. And stratification is like this. The graph that provides a stratification is precisely goes like this. There are 4 edges. There are 4 edges, 1 vertex, and 6 regions in this case. And if you look at carefully, this is in fact the dual of a usual triangle of the boundary of the 3 simplex. So how does it work? This duality, how does this duality works? There's this inside, there's a 3 cell. Its dual is just 0 cell, and that's this one. And from this single cell, we have dual 1 cells out of each 2 cells. They're precisely these ones, if you look at carefully. Now, whenever we have 1 cell, we need to assign some region, okay? And that's precisely this region. Yeah. So it is like, this is the face, that case. So this is precisely the dual, and there are 6 edges, and there are 6 regions in this case, and there are 4 faces, and there are 4 edges. Okay, what is skeleton of a closed 3-manifold? A skeleton of a closed 3-dimensional manifold, M, is an oriented stratified 2 polyhedron, P, which is embedded in M such that the boundary is empty. There is no boundary, there is no edge with only 1 branch. Okay? There is no edge, just staying inside. Well, what is oriented stratified polyhedron? We say it's oriented, that means each region is oriented, so there is no requirement like global orientation, like compatibility. Each region can be oriented differently. It's not matter. The only consideration is that each region comes equipped with some orientation. There is no compatibility condition. So, and pay attention that edges are not oriented. Edges are not only regions. Interiors of each 2 simplex is going to be oriented. And we denote, and such that the condition is that the complement of this stratified 2 polyhedron in M is disjoint of 3 open 3 balls. And we denote as number of these balls is absolute value of M minus P. So a skeleton of a closed 3-manifold is an oriented certified 2-polygon. Its complement is disjoint of open balls, which you can think of precisely like this. This is a very first example that comes into mind. Okay, this is certified 2-polyhedron, and its complement consists of precisely open 3 balls, which what we removed above from the triangulation. So but there are of course more general skeletons. Okay, let's consider for S3, for example, 2 vertex and 2 regions and 2 faces. In this case, there are only number of 3 balls is just 3, the inside and the outside. And for S1 cross S2, one fixes points in S1 and a loop in S2, then this union, A cross S2 union S1 cross L, is a skeleton of S1 cross S2, and again, number of P balls, 3 balls is 2. One is inside in this one is outside. Okay. So in this book, they study trio and realization, they study skeletons. In the blue book, if you look at, in the blue book, there's also state some version. There they study, trio studies more on spine of 3-manifold, which is kind of special case of spine is if this number is 1, maybe I should have said, if this number is 1, then it is a skeleton becomes spine. Spine is kind of more specified version. This is more general than spines. And the primary moves, they define, of course, they're going to take a skeleton. From this, they're going to put some combinatorial data from a spherical fusion category. But this, whatever we are going to assign, it must be independent of the choice of initial skeleton. So they come up with this primary moves that relates any two sufficiently enough primary moves, local moves that relates any 2 skeletons of a 3-manifold. And they look like this, like attaching a bubble and getting rid of an edge and contracting 2 vertices along an edge. And this is like pinching this region into another region. These are all, and then one can consider their reverses as well. They're also inverses. So primary moves are those primary moves or skeletons of the collection of skeletons of M are orientation preserving isotopies of these skeletons and plus these moves. And they prove that, which is not very easy, it's constructive for various pages. They prove that any 2 skeletons of a 3-manifold can be related by primary moves. So whenever you pick P and P prime, there are finitely many, other than ambient orientation preserving ambient isotopies, there are finitely many primary moves consisting of these T0, T1, T2, and the T3, and their inverses one can relate from one to another. And one step at the end, when they define their invariance, they need to show a way that whatever the number is assigned is invariant under these transformations. Okay. So next, let's study multiplicity modules and colored graphs. Okay. We fix a pivotal category, C. Then for any 2 objects in this category, a permutation map is the one that goes from home 1 xy, x tensor y, to home y tensor x. We do permutation on the source of this home set. So what it does, it takes alpha, right? Alpha is from 1 to unit object to y. What it does, the input is this thing, right? It takes this R and then swaps back in this one. And similarly, doing this is the same thing, taking this and doing this. Because by graphical calculus, these morphisms are invariant under planar isotopies, and so one can take this and rotate like this. When you do full rotation in the inside, you get this one. So they're equal maps. And in fact, these permutation maps are invertible. They're k-linear isomorphisms, and the isomorphism, their inverses are precisely pi y minus yx. It's a nice exercise to show that. It's a graphical calculus simply. Now, a tuple of signed objects. What does tuple of signed objects? One fixes an n objects of C and associates pluses and minuses, where epsilon I, here, when we say epsilon I is an element of plus or minus. So what does this mean? If we have x1, 1, it's going to correspond to x1. But if we have x1 plus, if we have x1 minus, it's going to correspond x1 dual. Since C is pivotal category, it's fine. Dual is well defined. Okay. From given any such tuple of signed objects, we get an object of category where plus means it's just same, minus means taking dual. And a K module that is assigned to this one, whenever we have such a tuple of signed objects, is preserved under cyclic permutations of S up to permutation isomorphisms. So whenever we have one to, let's say, x1 plus x2 minus xn minus, whenever we have this, one can do, well, they're the same, in fact. These are the permutation objects. Again, the same thing. 1 plus xn minus. So one changes the isomorphism stays the same, but it's on the cyclic permutation that is preserved. Well, sorry, this is not equal, but permutation is. So we call a cyclic set in a pivotal category is a triple where E is non-defined as set and C, and which has cyclic order, and we have two maps. The first one maps from E to objects of C, and the second one maps to plus minuses. So this is precisely generalization of this signed objects and whatever it determines. Next, we will use these things in like later in geometric ways. How to get cyclic C set. From cyclic C set, we get permutation modules, and we are going to use them to define invariant of the manifold. Okay, whenever we have a cyclic C set, okay, we define a multiplicity module of E. Okay, how do we define this? We define, let's say, for any element in E, we have this morphism, right? This is a morphism in C. From the unit object to remember, C is an element from here. It takes an here, and then it gives an object in here. So this is an object in C, and this is plus or minus 1. But plus means don't change anything. Minus means take dual. That's the argument. So this is tensor product of n many objects in C. So we get this morphism. And in fact, this is we know that from the fact above that under cyclic permutations, this is invariant. So for any E and F, right? For any E and F in here, we get a permutation module. What it does, it takes like this one. And then if E is in here, F is in here, one does this all the way there. Okay. These isomorphisms relate these K modules all of the way, HE and HK, these are isomorphisms. And this whole system gives a projective system of K modules under this permutations isomorphisms. And its limit of this projective limit of this system is defined as HE. Or more precisely, in the product of these HEs satisfying these two conditions, where these are permutation maps or isos. It's just a direct limit, it's just a projective limit of this K modules, but it is nothing more than that. We always use the projection, so it's fine. Next, there's a lot of definitions, but please keep up with me. Like we're not that far. Now colored graphs. A graph G is C colored if its edges are oriented and they're endowed with an object of C called the color of this edge. It's like edge is oriented and each edge is equipped with a color of object of C. Okay? Maybe as an example, locally, if we have this, C1, C2, C3, C4, C5. And I don't know what happens. Must be a graph. A C colored is like oriented edges plus plus each edge is colored by object of C. Next, we define multiplicity modules and colored graphs. Oops, sorry. Yes, no. Okay, next. Yeah, okay. We define this colored graph. So we are given an oriented surface, and a C-colored graph in C is just a C-colored graph embedded in sigma. So this was more general, but now one can embed it on some surface. Again, just a graph embedded on a surface whose edges are oriented and edges are colored by objects of C. And next, we are in vertices. A vertex of a C-colored graph determines the cyclic C set. Okay, how does it do that? When we fix a vertex of such C-colored graph, we are going to define a cyclic object. So let's say this is oriented surface, like this. So whenever we pick a branches, right, there are branches in here. So what do? We go through the opposite orientation. Okay, and it is going to give among the regions cyclic order. Whenever you start, it doesn't matter. If you start in here, that's why it's cyclic. It doesn't matter where you start, but it's going to give a cyclic order. And more precisely, the cyclic C set consists of EV is a set of half edges incident to V. Okay, and half edges precisely half edge. Whenever we have, I will go over an example, but say this, we have a graph, and half edge. This one, this is precisely this one. So elements are half edges, and cyclic order induced by the opposite orientation of sigma, as I said, and the map given by this half edges, the objects of C, it takes assigns the half edge to the color of the edge that G containing E. And this map is assigned to whether this assigns the plus or minus to each half edges, right? It assigns plus if E is oriented toward me or otherwise. In this case, we have these are half edges, right? And then this is the color that we have, right? C1 is the color. And then for this half edge, is this is minus, this minus, minus, plus, minus. Okay. It assigns plus if it's oriented toward me, minus otherwise. Okay. Next, when we have a multiplicity module, that's our definition. When we have a graph at vertex V, we denote this to be multiplicity module of EV, okay, which is, remember, 1 from 1 to C1 plus minus Cn. And next we take tensor product of unordered tensor product of over all vertices. Since this is a multiplicity module, is a projective module, is a projective limit, then we have projection maps from this to each of the components. And they're going to look like this. We consider this multiplicity modules as their component precisely looks like this in the graphical calculus as we had above, like this. There's nothing in the bottom because source is unit object. On the top, we have these objects. And it is plus if it's oriented like this. It is minus if it's oriented like this, which is compatible with the graphical calculus that we had at the first lecture. Remember, when we have a pivotal category, f x, y, this was f x to y. However, if I draw, let's say x, then this is our g, say, g is from x to y star. If it goes away from g, then we need to take dual, which is minus in here. So one should consider this as a vertex in this case. Now it will become clear now when we do that. Now consider this as an example. We have a surface and locally graph looks like this. There are 4 edges at a single vertex. And now we are going to define this multiplicity module, this component. Let's consider at V, okay, G. This is isomorphic starting from here, let's say, okay. We go around like this. This is the cyclic orientation. It goes from 1 to, first we come with I, but I is plus, right? It is directed toward V, plus, minus, plus, minus. And remember, since there's a colored, C-colored graph, I, J, K, L are objects of C. Okay? So in particular, if you start from here, our cyclic order, it is I, J dual, K, L dual. Okay? That's how we get this permutation module. But this is isomorphic by a permutation isomorphism to the following. If you start from here, okay, J dual, K, L dual, I. Okay? Isomorphic by permutation isomorphism. Or I can start from here, and then it's a form from 1 to K, L dual, I, J dual. Or similarly, one can start from here. And if we have this union of graphs, it's just the tensor product of these K modules. Remember, these are elements of C, and C is K category. So each of them are just K module. Remember, K category means morphisms are K modules. Okay, maybe okay, let's go over this and then give a break. Okay, now let's fix G colored let G be a C colored graph in R2. Again, remember in the Witten-Rashelkin trial case, we study operator invariants of ribbon graphs in R3, R2 cross I, when we just associate to them some operator invariants. And now we do the same thing. We have a graph in R2. We are going to associate we are going to associate to them the operator invariants using graphical calculus. And then we are going to generalize them using skeleton of 3-manifold to invariant of 3-manifold. Well, let's do it in R2. Let us let G be a C-colored graph. So remember, what does that mean? We have a graph which is its edges are oriented, and each edge is colored with some object of C. Okay? Now for each vertex of G, we pick a half edge and deform G near V so that the half edges incident to V lie above V. Okay. Remember, we have something like this. Let's say again, object I, J, K, L. Okay. So what do? We deform this graph. This is a piece of the graph, okay, at the vertex V. I don't know what happens on the side. Near V, we deform it so that this half edges, right? These are the half edges. These are the half edges. They're going to stay above V. Okay? So we're going to do this one. Like I, simple. There's another unique way of doing it. This is L, J, and K. Everything stays above V. Okay. Now, and then we're going to put here the corresponding module. Okay. And when we pick EV, in this case, I pick this one. So then EV is going to stay in the leftmost side. There's kind of a choice, but it's independent on the permutation modules. Let's see an example. Like for example, this one. In R2, we have this orientation. We fix this. Now we are in EV. Okay. Now what we do, we move everything up. Okay, we move everything above in the second corner of R2 to above the vertex, so that EV, the chosen half edge, is going to be on the leftmost one, like this. This is the picture. Then here we are going to put the projection of this multiplicity module at alpha V. Okay, and then remember, when we do this, then pick any alpha V and replace V by a box colored with this projection of module, then of the universal cone, then we get a Penrose diagram without free ends, because graph, there is no end, right? There is no, this is going to get some vertex. At that vertex, we are going to do the same thing. This is going to end up within some vertex. This is going to be centered. So this graph doesn't have any ends. Okay? That's why it's going to be closed graph. And the graphical calculus says the result of this thing is going to be endomorphism from 1 to 1. Okay? What we do for each edge, we do this operation, and then we replace there by the permutation modules, and then we get something, a graphical calculus and endomorphism of 1. And the image of this thing, so we have a spherical, we have a pivotal category. So this precisely gives, from this permutation module, an endomorphism from 1 to 1. If this category is fusion, this is K, so it's going to assign a number. Okay? So if you pay attention, so this is precisely is an element of a G dual. It takes an element and it gives a number. And the lemma, it says this homomorphism is well-defined isotopy invariant of the C-colored graph in R2. This is exactly the corresponding statement for operator invariance of ribbon graphs. In this case, we have graphs and C-colored graphs in R2, and this is the operator invariant of this graph. And whenever we have isotopy, we get the isomorphism. Okay, maybe we can give a 10-minute break and then do a specific example and see everything on an example, what is going on, at least in the R2 case. Okay, let's just, I gave a lot of definitions and notions and things. Maybe things just at the moment feel like complicated, maybe out of control, so many things. But in fact, what we are doing is not that complicated. So let's go over an example and see what we are doing in an example. So what we are doing so far, we have a pivotal category, C, not necessarily fusion at the moment. We have a pivotal category, and we have a graph in R, whose edges are colored, which is oriented, and they're colored by objects of C. X and Y are objects of C. And this graph is colored. And R2 is oriented in this way. So we're going to define this f of this graph. So what it is. So let's see. Okay, there are three half edges. The one is this half edge, and the other one is this half edge, and the third one is this half edge. One. There are three half edges incident to U, and there is one half edge incident to V. Right? They're just literally the half of the edges that we consider. Okay. Next, what is the cyclic order on this half edges? At this vertex, this half edges gives us the set. Okay, and we need a cyclic order. How do we do the cyclic order? If we start with E1, we follow the reverse orientation of the surface order or R2. Okay? We go the first this one, we go this one. E1, E2, and E3, and E1. Like following the orientation opposite orientation. So what are the cone isomorphisms associated with these edges? Okay, we have a permutation module, and then we have projections. Okay? Kind of isomorphisms. So in this case, E1, like at V, right? At vertex U, we have E1 half edge, right? So we start at E1 and go this one and this one. So, and what do we know? This is minus. It's leaving out of U. Here we have plus, right? And here we have minus. So it's X, right? This is, since it is minus, X dual, and X and Y dual. So X and Y dual. And the same way, if you do for U at E2, if we start from here, if we start our cyclic order like this, then we have X, Y dual, and X dual. And similarly, if we start from here, again, at vertex U, half edge E3, that we're going to start with half edge E3, that is this one. So this is going out of, right? So this is negative, it's not coming to you. So this is going to be Y dual, X dual, and X. How about this single half edge at vertex V? So this is coming here, so it's from 1 to Y. So this is positive, 1 to Y. And there are isomorphisms. So now they are all related, like in these three, right? These three, they are related by this permutation modules. For example, let's consider this one. Okay, it takes the image of this thing, for example, like when we take alpha, it takes when it takes alpha, it's an element in here. So it's a morphism from 1 to X, so Y dual tensor X dual. But how to get from this from the first one? If we start from, if you look at it, this is X, right? No, sorry, I made a mistake. This is, it goes like this, X. So this is precisely X dual. If you go from graphical calculus, this is X, Y dual. which is exactly what we have. So this is the input. If we take alpha in here, right, they're all the same things. Remember, the source are the same thing. If I pick an alpha in here, its image is in this one. So it makes sense. Now its image in here, how does it relate? We take this edge on the left, we put light modes. So we're changing the cyclic order. This is precisely corresponds to permutation module. So what is this operator invariant? Maybe or F, morphism under it. So this is for each vertex, we take tensor product, right? For each vertex, we have a permutation module, and then we take their tensor product. And for any alpha, beta in the morphisms, what is their images under this FC? It can be computed in various ways. For example, one is using, right, E1 alpha, like which is X, remember, this is X star, this is X and Y, or V. If we apply this one and this one, this is precisely endomorphism C of 1. Same for this one and same for this one. Right? And they compute the same thing, whichever we like. Because of permutation modules, they're invariant on the cyclic permutation, which is like these permutations. But this is all graphical calculus, the power of graphical calculus. That's all we are using. So we are given a C-colored graph from which we compute the cone isomorphisms. And the cone isomorphisms are all related. And from this, what we do, we replace this U depending on what we choose. Remember, we choose either like this or right? Like we make everything about these vertices. And that's precisely as you can see. This is how it goes. Okay. Now we can define state sum invariant of closed 3 manifolds, which is like straightforward. It takes also some more time. Let's go step by step. We fix a spherical now fusion category. Right? So far we didn't require fusion category, but we need now being a fusion category, fusion K category, whose dimension is now 0. It's invertible. And then we fix a representative set of simple objects. This is a choice we make. Here we have a choice. And then next we have a closed-oriented manifold, and another choice is choosing a skeleton. Okay, this is the second choice we make. When we are given a spherical fusion category and a manifold, we choose the representative of simple objects, and we choose a skeleton. And its regions we denote by reg P, and the coloring of P is like our state, maybe. The coloring of P is a map from regions to set of simple objects. So remember, this is like when we have triangulations, if we consider its faces, then that means labeling each two-face by some I and by some J, where I, J are simple objects. Which are either equal or not isomorphic, because they're elements of representative set. So coloring means coloring each two faces by simple objects. But don't forget, skeleton of M is oriented to stratified two polyhedra. So they are oriented. Okay? Two faces are oriented, not edges. So if we change orientation, what's going to happen? We're going to change their duality. That's the whole idea. If we change another one, but changing orientation of one of them is going to change the skeleton. Next. Okay, for any region, the object is called the color of the region R. See color of the region. And next, so far all of the, like, we can ignore this now. Dimension of a coloring, which is some maybe which does not make sense, but this is just a simplification. It does not mean geometrically anything. It's product of dimensions of the simple objects, right? This is for each region is a simple object. So what is its dimension? If it is, let's say, CR, we have CR, a simple object, its dimension is trace category. Right? And we take their product, and for each one of them, we multiply with the Euler characteristic of the region. So far, all of our regions were disks, so they were all one. But one can have something like this. One can have annuli. Okay? But let's discard it. That's not important. One can take this as one. Okay? At the moment, this is a special case, especially for the triangle things coming from triangulation. All regions are just disks. There is nothing interesting. Next, we define the crucial element, the scalar associated to coloring. Each coloring, we are going to get a scalar, and the idea is sum the scalars over all colorings. That's going to be the invariant. But this getting this scalar is not very easy. Okay, if this skeleton has no vertices, then this is defined vacuous case is like the one of the unit of the field. Assume P has at least one vertex, okay? Then since there's no isolated vertices in the stratified two-polyhedra, right? They're all faces of a two. They're all faces of a two simplex. So there is at least one edge connected. An oriented edge means an edge of P end up with an orientation. Okay? Remember, when we are given a skeleton, again, two simplices or regions are oriented, but not edges. So one can choose an edge for the one can choose an orientation for each edge. When we choose an orientation, together with the orientation of M, they determine a positive direction on a small loop in M encircling E. Okay. If we consider, let's say you are again, let's consider here considering triangulation. There are a couple of triangles. Triangles are glued, and for us the skeleton is just the two faces of this triangulation. So if you look at, for example, this edge, let's say we orient this. Okay. Then there are, in this case, there are three, right? There are one region, there are two regions, a second and third region, and there may be more. So the picture is like this, okay? Locally. And once we fix an edge, there are kind of regions nearby. With this orientation, let's say manifold is oriented right-hand rule, okay? Right-hand rule. This is the orientation of M. Then this right-hand rule gives, when we take a loop around this edge, there's going to be an orientation on this edge. And this positive direction is going to give cyclic order on the set of branches at E. Okay? Exactly. Whenever we pick an oriented edge, it has branches, and this orientation of the edge plus orientation of M gives a cyclic order on the set of branches. Remember, branches are germs of regions near E. Okay? Not number of regions, but germs of regions. It may be more than number of regions nearby at E. And to each branch, okay, in this case, number of branches, and in my example, like local example, number of regions is the same as number of branches. But if we had something like this, right, then number of branches is going to be one more than number of regions that are next to E. Now we assign a C color of the region by containing B and a sign equal to plus if the orientation given by B induced to 1 on the boundary. Okay? That means if you pick, say, remove this. If you pick an orientation of E followed by the one that inside in here, if this coincide this one, right? This case and this one, so they agree, this is plus. And now again, if you follow this and with this one, the orientation is given like this. It doesn't correspond. This is going to be, this is plus, this is minus. And similarly, if we take this one and the inside this one, the orientation is going to be this, and they don't agree, this is going to be minus. Okay? So each region is colored, and now we have pluses and minuses. We have precisely colored tuples of C objects. Okay? In this case, this is what I was trying to say. This is plus because we take first this and the second element is in here, and the orientation is this one. They agree. Again, I can do it. This one and this one, but the orientation with this one they don't agree. It's going to be minus, and here this one and this interior orientation. The orientation is going to be this one, and they agree, so it's plus. So this defines the cyclic C set. And this cyclic C set, we associate the multiplicity module because each region is colored by elements of C, the cyclic C set. We have a cyclic order, and each region has a C color, and then we have plus and minuses, right? And in this case, it's going to be, for example, it's going to be of this form, but for us, it's going to be home C. Let's start from here. Okay. 1, 2, our cyclic order is going like this one. CR1 plus, that means itself, and CR2 dual because it's minus. Tensor CR3 plus. In this case, we are going to, for each oriented edge, we are assigning a multiplicity module in this way. Once we orient the edge, we have canonical, and we have a canonical multiplicity module associated with that. And that is how we do it. Because as soon as we put an orientation on the edge, and together with the orientation of M, we get a loop, and then coloring gives the thing, and then this compatible with the orientations gives pluses and minuses, which is enough to determine cyclic set, which gives a multiplicity module. Okay. And there's a fact one needs to prove is that the dual of this whole tensor product over all oriented edges is the same as products of duals. And now for each unoriented edge of P, it's going to give rise to two opposite oriented edges. Okay. Now we did this for just one orientation. This is the first one, this is two, like E1 is going up, E2 is going to down. But what happens if we consider the opposite orientation? This cyclic order is going to reverse. And plus this is going to become minus, this is plus, and this is minus. This is precisely the dual of this cyclic C set. Okay, changing the cyclic order at the opposite orientation, and plus changing these epsilons to if they're pluses, they're minuses, they're plus. This is the duality between these are dual. So the fact that C is prefusion, whenever we have two such things, we can pair them by doing evaluations of each object that is involved, and this is going to be non-degenerate pairing. So since whenever we have a non-degenerate pairing, remember from the first lecture, when we have a K category with non-degenerate pairing, then there is a co-evaluation. Definition of a non-degenerate pairing is that there exists a co-evaluation such that we have this thing. And this is that image of like this correlation. There's a correlation map, and the image of one under this correlation is the star E in this tensor product. So here we are using fusionness. Okay. we are using that these dual things gives us this pairing co-evaluation element. That's right. Next, we take these things over all unoriented edges. So maybe I do it again. Locally, we are like this. So we have for each edge, right? For each edge, we have E1 and E2, and they are dual. Each edge defines us this duality pair for evaluation. And as you see, but what we started with here, it was unoriented edge. Okay? So for every unoriented edge, we get this one. And now we take tensor product of this over all unoriented edges of P. And they are vectors in this permutation module. Okay. So far we dealt with so far we just dealt with the edges. Next, what we do we assign some algebraic data to the vertices. Okay? For any vertex, we consider the link graph on the boundary of a ball near this point. So what is it? We choose a closed ball near this x, and we take intersection of this with the boundary with the graph with the skeleton, and this is going to give a graph on the sphere. Let's see what it is. Maybe if I get this one picture, I can show clearly. Where was it? Let's consider this one. Okay. Let's consider this is the vertex. So how do we get this graph? Okay, this linking graph. What do? We take a ball around this point, 3 ball. Then we consider its boundary. Okay, we take a ball neighborhood. This is just 3 ball, and we consider its boundary sphere. We take this intersection with the boundary sphere with the P. Okay, for example, in this case, what we're going to have in this intersection, we are going to have here an edge. Okay, and here there's going to be intersection. Here we are going to have another intersection. Here and then there an intersection. It's going to intersect in here, and then that's going to have on here. And this one. So there's this. But the point is, it's going to have on this sphere, we are going to have a graph. And it's going to look like there are 4 if you look at it carefully, it's going to this. So what we do for each edge, we take a 3 ball around it, look at its boundary, S2, we intersect this S2 with the P, with the skeleton. Then each region is going to give, be careful the dimension change, each region is going to give an edge. Now each edge of the skeleton is going to give a vertex. Okay? These are corresponding vertices, these are corresponding to the regions. So we have a graph on a sphere, and these edges are labeled by objects of C, because they're induced from regions, right? This is coming from this region, so it picks up that coloring of this one. So we have a C color graph on this one, and then according to the orientation compatibility, we give it plus or minuses of this orientation. And then in this case, so we get a graph, C colored graph on S2, but then graphical calculus, we have its associated operator invariant, right? So at each vertex, we look at the boundary S2. From there, we get a graph whose edges are colored by objects of C. And then by doing graphical calculus, it's an endomorphism of 1. And we assign this permutation modules. It's an endomorphism of 1. And then that's precisely just a number in this case. Okay, it's a dual to this one. So an example looks like this. This may look like locally, this is from the book. This is locally a P itself. Each region is oriented and they're colored by simple objects of C. Okay? These are regions and oriented, and there's a single vertex. What we do, we take a ball around the single vertex, 3 ball, and we look at its orientation, we look at its boundary. Then we have a sphere. This intersection of the sphere with the P is going to be like this. And again, by doing proper choice of orientation, we get orientation on the arcs. But now we have a graph on a sphere, and the edges are colored by the corresponding colors of the regions, because edges are induced by regions, and vertices are induced by the edges of the skeleton. And if you take a projection, we get something that is on the sphere, a graph. So for each one, when we do replacement like this, we get an endomorphism of 1. Okay, endomorphism of C of 1, and that is going to be the image of. But the crucial observation is the following. So if you look at every vertex right here, at every vertex coming from here, but this vertex comes from an edge, right? This edge we assigned before when we choose two orientations, we get dual permutation modules, and then so they have non-degenerate pairing, and the pairing has an inverse, we get CE. But if you look at this one, this is exactly this permutation module is from C1 to whatever, right? The simple object. This is going to be same as for this one. If you look at it, whatever there is nearby, this has the same. When we look at it as a C graph, which is the same cyclic C set. So this is precisely dual picture. At the beginning, we consider edges. We give two orientations, and we show that they pair, they agree. And now we consider vertices, and from a vertex, we kind of get a graph on the boundary, but on the graph, this vertex of this graph comes from edges of the skeleton. So they really match. And in this case, we get a canonical isomorphism. In this graph, for each vertex on this graph, okay, the corresponding permutation module overall E is the same as what we had before permutation module for the corresponding incoming vertex. And from this, we have the collection isomorphisms from vertices on the graphs of each link graph of each vertex to the oriented edges of P. So this is over all vertices, and this is overall oriented edges of P. And the fact that they agree, there's this isomorphism, and the corresponding multiple modules agree. And in this case, we have a dual vector. Whenever this is a dual element, whenever we pick an element in here, which is given by this operator invariant, it's going to be some vector is in here. And next, we are going to evaluate this dual vector at C. Remember, the C was the tensor product of star E, where E is unoriented. Right? At the beginning, this one. Coming non-degenerate of the pairing gives us this inverse of the pairing. That's what we evaluate. And this is precisely the scalar number that we get. We associated to scalar that is associated to coloring C. Remember, coloring is map from regions of P to set of representatives. Okay. And next, this is the thing that we want to study. So given a closed, we start with a closed-oriented three-manifold M. So we have a dimension of the spherical fusion category that we defined before. And here, this is the number of free balls in M minus P. And we remove the skeleton. And this dim C that we have seen is the product of dim of CR for each region, right? Region of P, and maybe plus minus some coloring of the region, Euler characteristic of this. And we multiply this with this scalar that is associated with the coloring. So this is overall colorings, runs over all colorings. And it is finite. Why it is finite? Because what is a coloring? Remember, let's write again. Coloring C is a map from regions of P to set of representative of simples, but there are finite many. This is finite. There is no condition on this map. They're just set maps. There's no condition. Coloring is just a map from set of regions to set of representatives, and this is finite because well, this is compact. For that reason, it's finite, and I is finite because it is fusion. C is fusion. Only finite many isomorphism classes of simple objects. So we are doing a finite sum, and then it is a candidate. It is well defined. And the theorem says, by various people, this is a topological invariant of M. That means it is independent of the choices that we made. A choice that we made as a skeleton of M, and a choice that we made as a representative of simple objects of C. Right? Initially, this invariant is computed by Tri-Bureau for UQSL2, and it's generalized to spherical fusion categories, and then further studied by Tri-Realizier. And in fact, there are more people I should have added. Indeed. And the next theorem is, I will not say anything about it. This is a numerical invariant associated with a closed three-manifold, 1S, and it's multiplicative on the disjoint union. Because when we take disjoint of closed three-manifold, we pick two disjoint of two skeletons, and everything is multiplicative. So this number is multiplicative. And the theorem says this extends to a three-dimensional TQFT. So it's a functor from cobordism category. And there's one more extension. Is one of the points of this book is that this invariant extends to pairs where M is a closed oriented three-manifold and R is a ribbon graph in M. This is like in Wittgenstein try, we had invariant of a closed-oriented three-manifold, or we have an invariant of closed-oriented manifold with a ribbon graph inside. And in this case, this is achieved in this work of Trier and Realizier. They extended state sum to manifolds with a ribbon graph inside. So this is called that the chapter that I don't go over in the book, graphical TQFTs, graph TQFTs. They first study this TQFT and then extend to graphical TQFTs by embedding ribbon graphs in it. Okay? Well, this is the kind of upshot of this today's lecture, like state sum invariant. So I want to finish the lecture by making some analogy, by going back to first lecture. At the end of the first lecture, remember, we studied all kind of algebraic properties, all algebraic categories, modular categories, rigid, fusion, pivotal, spherical, and modular. And then we relate them, we make a connection between spherical ones and modular categories by the center construction. Whenever one has a modular category, there is a center of it, and it's defined by half braidings. I will not go over this one by one. And the center of C consists of this half braidings and the corresponding morphisms, which commuted nicely. And this is in fact a braided tensor category. Oh, see, this C is not braided. C is just a monoid category. This is a way to get braided monoid category from a normal, usual monoid category. Okay, ZC is braided. And if C is pivotal, then its center still being pivotal with the following careful calculus, or if it is spherical, it continues to be spherical, the center. And now we have a forgettable functor, whatever, and then like linear structures that can be preserved uniquely. And one important theorem is that the center of a spherical prefusion K category is ribbon. But the more important than when K is algebraic closed field and C is additive pivotal category, then ZC is additive pivotal braided fusion category whose dimension is the square of the dimension of the original one. But this one that we need, maybe under the same assumptions that K is an algebraic closed field, then if C is spherical, then ZC is modular tensor category. Okay? So remember, when C is spherical fusion category, okay, because fusion, so this is instead of it's jump from pivotal fusion, spherical fusion. So what do we get? When we have a spherical fusion category, we define this TQFT, right? State sum. TQFT. And on the other hand, when we have on anomaly free modular K category, right? ZC, then we define, remember, tau ZC, right? Surgery TQFT. And the straightforward question, are they related? And answer is yes. Okay, and it says these two TQFTs are isomorphic. Okay, on each closed manifolds, the numbers are isomorphic, and also on the surfaces, so they agree. The state sum TQFT defined from a spherical fusion category of non-zero dimension is the same as the surgery TQFT defined from its center of this category. This is really the combining picture of all these three-dimensional TQFTs, two different aspects of three-dimensional TQFTs. And yeah, lastly, what I said so far doesn't involve anything. I didn't say anything about graph. But remember, in both cases, one can consider three manifolds with a ribbon graph inside. This is already done earlier, like surgery manifolds with an extra linking element, which gives a ribbon graph, you get an orientation. And this TQFT structure extend to that. And trivialize extend this state sum invariant to manifolds equipped with a ribbon graph inside, and that in fact this all isomorphism extends to graph TQFTs. So preserving these ribbon graphs inside these 3 manifolds, this functoriality extends to this extra ribbon graph data. And that's all I want to say for today.